Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Have you ever built a fancy model, maybe for a science project or even just a complex idea in your head, and then wondered if it actually works right? Does it really capture what is happening in the real world, or is it just a pretty picture that is totally wrong? Well, that is a big question in science too. And today we're diving into a paper that tackles this head-on, especially for those of us who work with data in fields like psychology. It is about making sure our scientific models aren't just making stuff up, but are actually useful tools for understanding the world. This paper is all about a clever way to check if our statistical models are any good. Think of it like this. When you are building something, you don't just put it together and assume it is perfect, right? You test it, you poke it, you prod it, you see if it holds up. Scientists do the same thing with their models. But the paper points out a really unsettling fact. A lot of research, especially in psychology, just doesn't check if their models are wrong, and that can lead to unreliable findings, meaning we can't really trust the conclusions. So, what is the problem with checking models? Well, many of the easy standard ways of checking models only work for certain types of data, like the kind you get from a straightforward straight-line relationship. But in psychology, data is often messy. It is not always a perfect bell curve, and the relationships aren't always simple. This means those old-school checking methods often don't even apply, leaving researchers in the dark about whether their models are actually representing reality accurately. The paper highlights that traditional residuals, which are basically the errors between what your model predicts and what actually happened, can be really unhelpful for many types of models, because they can't possibly come from a normal distribution, which is a common statistical assumption. This is where the cool part comes in. The researchers introduce a method using something called randomized quantile residuals, and a handy R package called DHARMa to help us do this. Now, don't let the fancy name scare you. The basic idea is pretty neat. Imagine you have your model and it makes a prediction for each data point. DHARMa takes your fitted model and actually simulates a bunch of data based on that model for each of your original data points. It does this many times. Then it looks at where your actual data point falls within all those simulated possibilities. Essentially, it is creating a standardized measure of how surprising your actual data point is, given your model. If all your predicted values are pretty close to your actual data points, then these residuals should look like they're coming from a random, uniform distribution, like a perfectly fair coin flip each time. But if your model is missing something important, if it is not capturing the true patterns in the data, then these standardized residuals will show weird patterns too, like clusters or funny shapes. DHARMa then visualizes these patterns for you, making it super easy to spot when a model is misbehaving. Let's look at an example. They created some simulated data to show how this works. Imagine we're looking at whether the number of years an employee has worked at a company predicts if they'll quit. Now, it is probably not a simple straight line. Maybe employees quit early on if they don't like the job, and maybe they quit much later for life events like retirement, but in between they might stick around. So, they simulated data that captures this kind of U-shaped pattern, where the probability of quitting goes up at the beginning and end, but is lower in the middle. This plot here shows the simulated data. You can see the response is either 0 or 1, meaning they either stayed or quit. Notice how the quit responses, the ones are kind of spread out at the outer edges. But there are a lot of stay responses, the zeros, in the middle. This hints at that nonlinear relationship. Now, what would a typical researcher do? They might use a standard linear model called OLS regression. But the paper says this OLS model is likely wrong for this kind of data because it assumes a straight-line relationship. A better approach for yes-no outcomes is logistic regression, which they fit next. Here is the DHARMa output for the OLS model. Look at the QQ plot on the left. See those dots? They're supposed to be on that line, but they're clearly not. They form these distinct humps, showing the model is way off. And the plot on the right, the residual versus predicted plot, also shows clear patterns, not just random scatter. This tells us the OLS model is definitely not a good fit. Now, let's look at the logistic regression model. The QQ plot is much better, the dots are closer to the line. But the residual versus predicted plot still shows some curves, meaning there is still some pattern left over that the model isn't explaining. So, it is better but not perfect. To capture that U-shaped relationship better, they suggest a generalized additive model, or GAM. This type of model is super flexible and can handle curves and wiggles in the data. And when we check the residuals for the GAM model using DHARMa, wow! The QQ plot shows the dots hugging the line perfectly, and the residual versus predicted plot is just a flat, boring scatter. This tells us the GAM model is a really good fit for this simulated data. This plot here beautifully visualizes what the GAM model is doing. It shows that the probability of quitting has that U-shape exactly as they simulated. It is a fantastic illustration of how DHARMa helps us see when a model is truly capturing the data's underlying story. But this isn't just for made-up data. The paper also looks at a real-world example. They examine data about countries, looking at things like population area and the number of languages spoken there. The big question is, does the ecological diversity of a country predict the number of languages spoken within it? First, they tried a simple OLS model, just like before. And just like before, DHARMa's diagnostic plots revealed major problems. The QQ plot is all over the place, and the residual plot shows clear patterns of departure from what a good model would look like. This OLS model is definitely not telling the whole story. Okay, so language counts are discrete numbers, meaning you can't have half a language. So a Poisson regression model might be a better fit. This type of model is designed for count data. They fitted that and checked the residuals. Unfortunately, this Poisson model also shows significant problems. The KS test is highly significant, and the dispersion test shows significant deviation. This means the model's assumptions are being violated, likely due to overdispersion, which is when the data's variability is much larger than the Poisson model expects. To handle this overdispersion and account for the fact that larger countries might naturally have more languages, they used a negative binomial regression model, which is more flexible for count data and includes an offset for the area. And look at the DHARMa plots for this negative binomial model. The QQ plot is pretty good, and the residual versus predicted plot shows no significant problems. While there is still a tiny bit of overdispersion, it is vastly improved, giving us much more confidence that this much better, more accurate representation of the relationship between ecological diversity and language counts. So what is the big takeaway here? The paper argues that checking your models is absolutely crucial for reliable scientific research. It is not enough to just run a statistical test and assume it is correct. By using tools like DHARMa and randomized quantile residuals, we can get a much clearer picture of how well our models actually fit the data they're supposed to explain. The authors emphasize that while no model is ever perfectly correct, we can strive to make them as useful and accurate as possible. This approach works for a wide range of models, from the simple to the complex, making it a powerful tool for social scientists. They've even created a whole website dedicated to this topic with more examples and explanations. It is like a super-powered instruction manual for making sure your statistical models are up to snuff. It really boils down to this science progresses, when we can trust our findings, and we can only trust our findings if we're confident that the tools we use, our statistical models, are actually doing a good job. This paper and the DHARMa package offer a fantastic way to do just that. It empowers researchers to be more critical of their own work, and in turn produce more reliable and trustworthy science. Now, for my take on this research, I think it is absolutely brilliant. The core message that we must check our models is so fundamentally important. And it is kind of shocking that it is often overlooked. The DHARMa package, as described, seems like a game changer because it applies one consistent method to so many different types of models. That generalization is key for making these checks accessible to more researchers. The biggest strength here is the focus on practical application and clear visualization. The examples, both simulated and real world, really drive home the point. You can see when a model is bad and when it is good. That's so much more helpful than just looking at abstract numbers. The limitations, as the paper implies, are that even the best models are still simplifications of reality. The more complex your data and your research question, the more subtle issues might still hide. Also, while DHARMa makes it easier, understanding why a model is misspecified still requires statistical knowledge. It is a diagnostic tool, not a magic wand. For the real world, this means we should be more skeptical, in a good way, of findings that don't mention model checking. It also means researchers have a powerful new tool to improve the quality of their work. Imagine studies in clinical psychology or education that are more accurately reflecting the complexities of human behavior because the underlying models are properly validated. Future research could definitely expand on this, perhaps developing even more specialized DHARMa checks for very specific types of data or models, or integrating these checks more seamlessly into statistical software. What do you all think? Have you ever encountered a study where you wondered if the model was actually right? Let me know in the comments below. And if you found this breakdown helpful, please give this video a thumbs up, subscribe to RUBIN'S Mind Lab for more science insights, and hit that notification bell so you don't miss our next dive into research. Thanks for watching.